Today we're very excited for the third part of Professor Teissier talk on a geometric introduction to the theory of valuation via infinite dimensional algebraic variety.
Thank you very much. Before really starting, I would like to give an example of what I was talking about yesterday. You remember about deforming or specializing a curve to its associated graded ring, which is a monomial curve. And I give you the archetypal example, which actually started me on this track many, many years ago. It is a plane curve, and I will give it to you in coordinates u1 and u2 because, so u2 squared minus u1 cube squared minus u1 to the 5 u2 minus 1 over 16 u1 to the 7 equals 0. You recognize the equation of a plane curve. You may also recognize that it is irreducible. And what you may not recognize at first sight is that it is completely impossible to resolve this curve by a single toric map of the plane. Because in the terminology of the Russian school, it is degenerate with respect to its Newton polygon, whichever coordinates you take. One reason is that it has two Puiseux exponents, and that decides the day. So, nevertheless, what I claim is that it can be resolved by a toric map after being re-embedded in a three-dimensional space. And let me show you that by telling you that this curve can also be viewed as follows: u2 squared minus u1 cube minus v times, well, the v will be between parentheses for the moment, and u3 squared minus u1 to the 5 u2 minus 1 over 16 v squared between parentheses. That's it. What did I write? u1 to the 7 equals 0. So if you take v equals 1 and you eliminate u3 between these two equations, you find this equation. So this is a space curve which is isomorphic to my plane curve. It's just a re-embedded. And in order, it can be, this presentation can be parametrized as u1 equals t4, u2 equals t6 plus 1/2 v between parentheses t7, and u3 equals t13 plus 1/4 v in parentheses t14. Okay, so the thing I mentioned yesterday was that you recognize yesterday on this white board, which was erased a few minutes ago, you had this, on my asking, you had this deformation of the parametrization of a space curve to the monomial curve. You recognize here a monomial curve, and you recognize here two binomials, which are the equations in space of that of the same monomial curve. So what I claim is that once my plane curve has been re-embedded in three-dimensional space like this, there exists toric map, birational toric map, Z to A3, such that the strict transform of my curve X in A3 becomes non-singular and transversal to the toric boundary. So that is the basic example, which shows the phenomenon. After that, of course, you can generalize this to any curve once you have understood the general idea. So, in order to convince you that one can generalize, I will give you an example of how to resolve a family of a binomial ideal, a family of binomial equations in a finite dimensional space. And then we deform them, and we see if we can continue to resolve the deformed equations. So in order to convince you, I cannot write down many equations, but the general idea is that I will have a sequence I have a weight on my variables. Usually, you know, all my variables have some weight. And here I add only monomials of weight strictly larger than the weight of these monomials, which is the same. So imagine that you have a finite collection of equations like this that I showed you yesterday how to resolve this part. And I want to show you now how you can extend the resolution to the deformed equations. But because it's a rather complicated proof combinatorially, I will show it to you in a special case where you have only one equation and the valuation is of rank 1, which means that all the values which I look at are real numbers. So if you trust me that this is sufficiently general, the general case combinatorially is quite complicated, actually. So I cannot even dream of trying to expound it on a blackboard. Okay, so let us start. So we have one equation, this one. We have a weight with real values. And we want to say something. So let us look at the cone in R, my number of variables, let us say M, generated by the vectors P minus N, such that, of course, Cp, so I erase the L because I have only one equation. So the cone generated by all these differences and M minus N. Okay, erase the L because there is only one equation. Okay, so let's call this cone E prime. Well, we have to deal with series in the sequence, so I cannot assume that this is a polynomial, and therefore there is a little problem that the cone generated may not be rational because it's generated by infinitely many points. However, the ideal generated by the UPs, the UP minus N, or UPs if you like, the ideal generated by the UPs in, let us say, the power series ring is finitely generated because we are in a Noetherian ring. So all the exponents that appear here are of the form UP1 plus something, UPS plus something. There's a finite number of generators. So I enlarge my cone. Let's call this cone E prime. What is? Oh, these are my variables. Okay? Oh, too many M's? This is a capital M. So I say that my cone E prime is contained in a cone E, which is generated by P1 minus N, PS minus N, and then the base vectors of the ambient space, and then M minus N, because all the vectors that I find, all the exponents which I find here, they are of this form. Because here I add some element of the first quadrant. And now you see that this is a finitely generated cone that generated by integral vectors, so it is a rational cone. Now, my weight gives me a vector. I look at the vector W of U1, W of Um, and this gives me a well-defined vector, which I call W, underline, in Rm. And by assumption, the vector, the scalar product of W and all the Pi minus N is strictly positive. The scalar product of W with the EI is strictly positive, and the scalar product of W with M minus N is 0, because we assume that M and N have the same weight, they are the exponents of our binomial. However, this cone here is strictly convex precisely because all the vectors which generate it satisfy this inequality, except the last one, but the last one I take only positive linear combinations. So you see that this cone cannot contain any vector space. Okay? So we take the convex dual. What did I call it? We take the convex dual, which is the set of vectors in the dual space, let's say U, in Rm dual, such that U of F is greater than or equal to 0 for all F in E. So E, F and E, those are now no longer integral points. These are vectors in a real vector space. Okay, but this is the convex dual of E. And so now if I look at the dual space, I have two things. I have the dual hyperplane, which we saw yesterday, Hm minus n. And we have this rational cone, which is the dual of a convex cone, which I won't picture because it's too complicated to picture. But the important thing is that the dimension of E hat is full dimension, because this is strictly convex. Dimension of E dual is a full dimension. And W, my vector W, which is a vector which I can consider as a, sorry, I should have considered it as a vector in Rm dual, because I evaluate it on vectors of Rm. And W is contained in H and in E hat dual. And not only that, but because all these inequalities are, it is in H because it satisfies W scalar product with m minus n equals 0. It is in E hat, in E dual, because it takes a strictly positive value on all the generators of E. So not only that, but it is in the interior of this guy. So let's put it. Of course, this means relative interior, because not interior in the total space, but it is in the interior of the intersection with H. Okay. Now we take a fan sigma, which is compatible with H, like yesterday, and E dual. And if we look now at one specific cone of this fan, this is a regular fan. We look at one of the cones of this fan. And in fact, I think I've shown you that yes, I did, this corresponds to a chart in the toric modification of the affine space. So this corresponds to a certain chart. That the points where I will see the strict transform of my binomial are the charts where, let me write it this way. Sorry. Let me. Yes. The monomial u to the m becomes, as we saw yesterday, okay. Now we can remark that the weight of u to the m, is that it? Yes. No, sorry. No, sorry. Because of this, we can remark that our vector W is equal to sum of W of yi times AI. We know that the matrix of the AIs has determinant plus or minus 1, which means that the weights of the y's are uniquely determined by the weights of the u's. And the formula which determines it, W is the vector W of U1, W of UM. And if you look at the formula of transformation, I should not have written this. I should have written UI equals sum equals Y1 to the A1I, Yn to the AIN. If I look at this, it tells me that my vector W, my weight vector, is expressed like this. And that the weight vector, that therefore the W of Yi, the charts in which I'm interested are the charts where the W of Yi are not negative. Because that's the only charts where I have a chance to see the strict transform of my binomial by the toric map. But you remark that to say that the W of Yi are negative, this is the same thing as saying that my vector W lies in sigma. Because sigma is the cone generated by. So we are going to be interested only in the cones of our fan, which contain sigma. But so W is in here. We want a cone which is compatible with H, compatible with E hat, and which contains W. So the picture is a little bit complicated, but W is here somewhere in this hyperplane. E hat, I don't dare try to draw. But what this tells me is that I can certainly, because my fan fills the space, the intersections of my fan with the hyperplane and with E are going to fill the intersection. So I'm going to find a cone which contains W, lies outside sigma, and because W is in E hat, and my cone is compatible with E hat, what does it mean? It's just like a hyperplane. You can imagine that E hat, it's a cone. It divides the space into two parts. And what I'm saying is that because my vector W is in the interior of E, the whole cone sigma has to be in the interior of E. So, so my cone sigma lies in the interior of E hat. It lies, and it is on one side of H, like yesterday. Okay? But because sigma is in the interior of E hat, it means that my vectors, it means that all the vectors which generate sigma are in the interior of E hat. It means that all these vectors, when I take the scalar product with the p minus n, I get something positive, or at least non-negative, but positive, in fact. Okay, is that clear? Because it is in the interior of E hat. So all, and there exists such a cone because E hat is of maximal dimension. Okay, this has to be recorded. But what does it mean? It means that when I write the strict transform of this equation, I write y1 to the a1n dot dot dot. Okay, I won't write everything. Then I have y1 to the a1 m minus n dot dot dot, the same thing, minus lambda. And then I can factor out y to the p minus n. Exactly. Y1 to the, well, I write this just y to the p minus n. Because W is, okay, it means exactly that I can factor out on my cone, on the chart corresponding to my cone sigma, I can factor out A1n, etc., from the transform of U to the P. And I win, because it means that the strict transform of the whole equation is the deformation of the strict transform of its binomial part. Thank you. Is it clear, or should I say it again? Because of this, I have transformed, by this geometric argument, I have transformed this assumption into the assumption that I have a cone sigma, which is regular, which is of maximal dimension, and such that all the AI p minus n are positive. So the AI p minus n are the exponents which I have here. I should have written them. A1 p minus n, and so on. So it means that these exponents are positive. It means it's lawful to factor out this part, and it means that the strict transform of my equation is a deformation of the strict transform, and therefore it is non-singular. Well, there is a little detail. You have to verify that this is indeed, the weights are larger, but it's practically obvious. So this is how you transform the existence of a deformation, of a resolution, of a toric resolution of a binomial variety into the existence of a toric resolution of certain deformations of the binomial variety. This is what one has to remember. And of course, you see that if I can do this for one equation, I can do it for finitely many, because of finitely many cones and so on. Then, of course, I have to check that the intersections are transversal, but this is the same trick as yesterday, which is just a little bit deformed. And now I want to, so I hope convinced you that in this situation, we have a kind of, we do not resolve here. We just have a point where the center of the valuation has become non-singular. Okay? It tells me that the transform of my equation here is non-singular at the point which is picked by the valuation, or at least, because you see this non-singularity does not need to extend to the whole chart. It just extends, it's just true in the neighborhood of the point picked by the valuation. It doesn't have to be true on the whole chart. Okay, so now how do we reduce? Which general case can we reduce to this relatively nice special case? So you apply this here, and you see that if you can resolve this, you can resolve the deformed equation by a toric map, and that gives you the assertion I mentioned in the beginning. So let us try to formalize this a little bit. A weight on a power series. So I start with same object, power series in m variables. A weight W is a map from n to the m to a totally ordered group, totally ordered abelian. Actually, because this is finitely generated, one can reduce this to a finitely generated abelian group, of course. But I won't go into this because it takes a little time. And so let's call this map, B. And W of a monomial, is B of M. So often I will just write W of M. B and W are so closely connected that one can confuse them. So this means only that any monomial has a weight. And then you can define with this evaluation by saying that the weight of a series is the minimum weight of its term. And this has a meaning because this is a Noetherian ring. So the semigroup of values, which is the image, so gamma, which is the image of n to the m, is a well-ordered, anyway, semigroup. This is all we need, in fact. So we can talk about the minimum weight, and that is the weight. So this corresponds to giving a valuation, which is a monomial valuation. You can say that on the same by saying it gives a monomial valuation. Okay. I define weight only to be able to define overweight. And overweight is exactly what I wrote. So an overweight deformation of a binomial ideal, no, I put the L's back. I have finitely many binomials, and I look at finitely many equations, which I call FL. It's this, with the condition that the ideal, that the FLs form a standard basis. This is very important. Standard basis of the ideal of K of U, which they generate. Which means that If I look at any element of this ideal, it has, with respect to the weight, it has an initial part, and that initial part is in the ideal generated by the binomials. This is not automatic at all. So it is an extra condition which says that by deforming the equations, actually, I'm making a flat deformation. If you just deform equations, what you get is an unfolding. If these initial forms did not generate a complete intersection, then the dimension may drop, for example, when you deform. We don't want that. So we impose this condition which says that the deformation is flat, in fact. So this is an overweight deformation. And the next step is an important one, that if I have an overweight deformation, let me call the ideal F, the ideal generated by the FRs. Proposition is the following: that the weight W induces a valuation on the quotient divided by F as follows. Take any element in the quotient. Let's call this guy R. Take X in R. Look at all the elements in the power series ring which have X as an image. Then the maximum weight of an X tilde, so that X tilde maps to X, defines evaluations. This is a non-trivial statement. If you have evaluation whose value group is a subgroup of R, then it is easy. Otherwise, you have to work a little. I don't have the time to explain the proof. I just want to remind you I just want to remind you very quickly that when you have a totally ordered abelian group, there is a notion of convex subgroup. It's an element so that if phi is a positive element and phi is less than psi, which belongs to this subgroup, then this implies that phi is in psi. It's equivalent, this condition is equivalent to say that the map, the quotient map, there is an order on the quotient which makes this map monotonous. The illustration, I told you the other day that you had to memorize Z2 with the Lex order. In Z2 with the Lex order, there is only one convex subgroup, which is the vertical line. Okay. Because if you have an element here which is less than an element, if you have any element, positive element, so positive, you remember, they're like that. If you have any positive element which is less than a positive element, there are not many places where it can be. Okay. This is an extremely important concept. It's very easy to prove that the set of convex subgroup is totally ordered by inclusion. So you have, in fact, you have a sequence of convex subgroup. And if it is finite, we say that phi has finite rank. And the rank is equal to the length of the sequence of subgroup. And the important thing is that rank 1, that means no non-trivial convex subgroup, is equivalent to saying that phi can be embedded in R as an ordered group. So in valuation theory, rank 1 is really easier, makes life a lot easier. In particular, to prove this kind of thing, in the case of rank 1, it's not very difficult. In the case of higher rank, one has to work. But I won't explain the proof because I have no time and it's not very informative. But you must remember that another thing is that if you take two consecutive convex subgroup, of course, the quotient has rank 1 if you take them consecutive, because there can be no convex subgroup between the two. Okay, so you have a sort of decomposition of any totally ordered abelian group into a sequence of rank 1 subgroups, quotient. You have a kind of what people call Bourbaki decomposition for a module. Okay, so, but this is an important statement. Let me give you the basic example again. Look at the two equations, u1 square minus u2 cube minus u3, and u2 square, simplified version of the one I gave a minute ago, u2 square minus u15 u2 equals 0. So let this be f1, let this be f2. You have to trust me that indeed, so this has weight 12, 13. Now, if I look in R, which is k of u1, u2, u3 divided by f1 and f2, take the element u1 square minus u2 cube. It has an image in here, and this element has weight 12. But there is another element which has higher weight and which has the same image. It's u3. Okay? So the value of the valuation will give value 13 because it's the maximum weight. And it's an easy exercise to see that an element x tilde gives the maximum weight if and only if its initial form with respect to w is not in the binomial ideal. And you see that it's true in this case because u3 cannot possibly be in the binomial ideal generated by u1 square minus no. Okay? So this is another very trivial but extremely important fact. In fact, in the whole theory, this thing, which is a two-line proof, plays more or less the role of the Weierstrass division theorem. So you might think the whole theory is trivial, but it's true that this is very, very elementary, but very important. Okay, so this is an overweight deformation. An overweight deformation gives me evaluation on the quotient. And what is the associated graded ring of the quotient with respect to this valuation nu? Well, guess what? It is polynomials in u1, um divided by the binomial ideal. Right? This is, in fact, also very easy to prove. So remember, overweight deformation, valuation on the quotient, graded ring is given by defined by the binomial ideal. Why is that important? Because here you have evaluation which is monomial. Here you have evaluation which is anything. So you have a relation between evaluation, which is any valuation more or less, in this case finitely generated semigroup, and a monomial valuation. In the history of valuation theory, people influenced by Puiseux, the Newton-Puiseux expansion, have always tried to embed rings into nice rings. Nice rings means essentially completions of semigroup algebras. Even if the group is very large, you can define semigroup algebra, you can find some kind of completion, and the generalization of the Puiseux theorem is take any ring with evaluation, let us say a rational valuation, can you embed it into some big field, and then something like that? Because this is what Puiseux does. Puiseux takes the ring of any curve, and it embeds it into something like that. So people have constantly tried to generalize this to that. And it works to some extent, but I claim that for local uniformization, it's not a good method. I claim, it's a claim, that the good method is to present your ring not as a subring of something simple, but as a quotient of something simple. Because then you have equations. Here, you have a parametrization. And the philosophy is that equations are stronger than parametrizations. Always. Okay, so let me try to prove my claim. So what do I want to prove, actually? Well, I would like to prove that if you take your ring complete. Right, in the right order. Noetherian, complete. Equicharacteristic. A new irrational valuation. With finitely generated semigroup. Then, nu is obtained by an overweight deformation. You see, here, overweight deformation, of course, I start with a power series ring. On the quotient, I have evaluation, which is obviously rational, with finitely generated semigroup. Okay? And now I claim the converse is true. If I take anything which looks like it could be gotten by overweight deformation, then it is gotten by overweight deformation. And in order to prove that, I'm going to prove a much more general theorem. Because it's the theorem which one can use even when the semigroup gamma is not finitely generated. Because I think, as I told you yesterday in the first lecture, the really important guys to study in this story are the valuations on Noetherian local rings, maybe complete, where the semigroup is not finitely generated, because that's where the difficulties really lie. Okay, so that's the first theorem. So now what is the theorem I want to talk about in general? I make a small introduction, which I won't write on the blackboard, because it's things that I think all of you know. It is the classical Cohen structure theorem. Here I'm reduced to the equicharacteristic case. The Cohen structure theorem is more general. It also works in mixed characteristic, but we'll leave that aside for the moment. So what does the usual Cohen structure theorem? It says that if I have a complete Noetherian equicharacteristic local ring, doesn't have to be a domain, then it is a quotient of a power series ring with coefficients in its residue field. Okay, that's the Cohen structure theorem. Do I need to write that down? So it's a wonderful theorem because it tells you that something which is a priori not geometric, the only quality it has to have is to be Noetherian and complete. Then it somehow comes from geometry because it's a quotient of a power series ring. So you have a kernel, and the kernel has equations. But if you look at it, the Cohen structure theorem tells you more. It tells you how to specialize your ring to its associated graded ring. Because once you have written down the equations, the initial forms of the equations, if you want to do it properly, they will generate the ideal which defines the tangent cone, which defines the associated graded ring. So the the Cohen structure theorem gives you a lot for very little. In fact, the only hard part is the proof of the existence of a field of representatives. All the rest is kind of direct. But once you have this field of representatives, you get a lot of geometry out of it. Okay, so what we're going to do is something similar, but in a different situation, of course, where we have evaluation. So I start with my ring R, which is complete, equicharacteristic, Noetherian, and I have a rational valuation. I'm not assuming anything about the semigroup. So the semigroup, as I showed you yesterday, is generated by a certain set of generators where I is an ordinal, which is bounded, in fact, it's bounded by something rather technical, which is the height in R of the valuation of nu. Okay. This is less than the dimension of R. Now, to each gamma I associate a variable, to which I give, of course, the weight gamma I. Then I look at all the sums of this kind. Okay, this is where E is any set of monomials, and DE are in some field K. Before I go on, I need to say something about the semigroup gamma. I told you it's well ordered. It has another quality which actually comes from that one, which is that it is combinatorially finite. It means that for any element of gamma, the number of ways of writing gamma as a sum of other elements, you can put coefficients or not, the number of ways of writing gamma as a sum, distinct ways, of course, as a sum of different elements is finite. In particular, it's something we are rather familiar with. If you want to write gamma equals gamma 1 plus gamma 2, there are only finitely many ways of doing that. What it tells me is that if I look at the map from the set of monomials, any set of monomials, it could be all monomials, to gamma, which to a monomial u to the e associate its weight. Okay, u to the e, that's u1 to the e1, or ui1 to the er1, and so on. So the weight is a combination of certain, the weights of the variables which appear here. He said this has finite fibers. Okay, this is an equivalent statement. So, because of this, I can multiply two series like this. Okay. So, the set of those series is an algebra, is a K algebra, which I write Ek of gamma. In my papers, it's written like this, but finally I got tired of writing this. Okay. So let's call it Ek of gamma. You must realize that it's a big algebra because you have infinitely many monomials and you can take any sum, so it's a big algebra. However, it behaves in many, many ways like a generalized power series algebra, and that is the way you should think of it. For example, it is a local ring. For example, if you have an element h of u in Ek of gamma without constant time, it's a local ring. Of course, the maximal ideal is the series with a zero constant term. If I take a series which is in the maximal ideal, then I can substitute in another series. Substitute for any monomial in another series. So it has a number of nice properties like that, which I will not enumerate because I'm getting short of time. But the proof of each of these properties is not completely obvious unless the group is of rank 1. Because if the group is, what does it take for a series? All these consist in making sums of series. When does a sum of series belong to the ring? If and only if every monomial appears only finitely many times. So you have to check that whenever you want to prove something, all you have to check is that monomials cannot appear infinitely many times. Another very nice property which it has is that it is what people call spherically complete. Because the weight W can be used to define a ultrametric by taking the weight of the difference. And so you can think of this as define some kind of metric. The balls are of the form a series and a ball is of the following form, all the elements x, such that W of x minus a fixed center is larger than or equal to some gamma. So this is a ball with center A and reduced gamma. But remember that gamma is in a very large set. So spherically complete means that if you take any set indexed by an ordinal of balls, non-empty balls, which are nested, and non-empty, the intersection is non-empty. Roughly speaking, it means that every approximation process which you might dream of will produce a result. So, just like the implicit function theorem or this kind of thing for power series. Okay, but I'm short on time. So let me tell you what is the valuative Cohen theorem. Well, the valuative Cohen theorem says, okay, I start from R. It's complete. Again, I must remember this is important. Equicharacteristic and Noetherian. Then I have the semigroup. Then I build this algebra. Then the valuative Cohen theorem says this. Say, pick generators of the graded algebra. Okay. We know that these generators are in bijection with the generators of the semigroup, and also, therefore, with the variables. Okay. Then the first part is there exist, and here the emphasis is on exist, psi I representatives in R, so that the initial form with respect to nu of psi I is psi bar, such that the map from Ek of gamma to R is well defined, continuous with respect to weight and valuation filtration, respectively, surjective, and what more? Ah, yes. If I look at the filtration, the associated graded ring, I get this. The associated graded ring of this is the polynomial ring in the UIs. Because if you take any element, any series, because there are only finitely many elements of a given weight, the initial form will be a polynomial. So this is the polynomial ring. And of course, the map which I get here is the map which turns UI to psi I bar. And it is the surjective map which presents my graded ring as a quotient, and whose kernel is generated by my beloved binomials. Okay? The map, oh, sorry, yes, the map, it's defined by sending UI to psi I. So you must see that this, it is not true for, in general, it is not true for an arbitrary choice of the representatives. Because you are only talking about representatives. So to every, suppose you have a set of representative psi I which is good, and to each one of them you add an alpha, which is infinitely small with respect to psi, so that it does not change, it has the same initial value. Then you take the sum of all these guys. This is not going to exist. So you have to be very careful in the choice of the representatives. The theorem is there exist choices, not just one, but there exist choices which will work. And you must think that the series sum of UI exists in my algebra. So this means that the series sum of psi I must exist in R. So it means that even though the i's live in an ordinal, they must be in higher and higher powers of the maximal ideal. This sum must make sense in the ring. Okay. All this has to be considered and overcome, but it works. The proof is complicated, except in rank 1, except if the valuation is of rank 1, the proof is rather complicated. In rank 1, the result, I should mention that, the result is a rather easy consequence of the theorem of Chevalet, because the theorem of Chevalet says that because the ring is Noetherian, in the case of rank 1, the p phi, actually in the case of rank 1, I is equal to omega. I always has to be the set of integers. So then there is a theorem of Chevalley which says that because the intersections of the P phi are 0, the P phi are contained in higher powers of the maximal ideal. That's the Chevalley theorem. It's a really wonderful theorem. N of phi tends to infinity with phi. So this, for example, tells us that the sum of the psi I exists, of course. But in the general case, you have to work much more than that. You work by induction on the rank. Okay, but this is just the first part of the theorem. The second part is what makes it really useful. It's about the kernel of this map.
So is this your theorem?
Yes.
Just check.
Oh, yes, sorry.
I want to make sure it's not Cohen's.
Well, you see, what is Cohen's theorem? It tells you something similar.
Yeah.
You know.
How old is this?
Oh, the first version is pretty old, but it's also a bit complicated. 2011? Well, anyway, it's in my paper, which was published in 2011.
That's not old.
No. And now, but the second part is really what makes it useful. The second part is about the kernel. And the second part is, it begins again, there exist. And again, this is a keyword. There exist overweight, I should say, given a system of generators of the kernel of the graded map. So given a system of generators, there exist overweight deformations of the binomials so now we're talking infinitely many equations, of course. Okay. Concept FL. So these are elements in the ring, in my such that the kernel, two things. First, the kernel of my map is generated up to closure by the FL, by the ideal generated by the FL. Okay, this is the first property. And second property, each FL involves only finitely many variables. Okay, I won't go into the proof. Again, it's very long. But I want to insist that you have here a ring which is very far from being Noetherian. You have here a Noetherian ring. So the game is to lift the Noetherian properties of R to the non-Noetherian ring. Okay? Just to give you an idea, you take an element of the kernel. You want to show that you can replace it by another element which has the same initial form but involves only finitely many variables. You push it forwards into the ring, you know it's equal to 0. But then when you write it out, you have certain psi I which intervene. Now you remember that your ring is Noetherian. So the monomials in the psi I are a finitely generated ideal. So you go back up and you twist a little bit and it works. The real messy part is to prove that you can generate like that. So this is a theorem in two parts. You don't have to worry. You don't have to worry about this in the usual Cohen theorem. It's automatic, of course. But okay, before I finish, so I want to. This is the general theorem. It is, I think, quite general, and it's a very powerful tool to study the general rational valuations. In the few minutes that I have left, I only want to show you how it's used in the case where the semigroup is finitely generated, because after all, I said this was the purpose. So in the case where the semigroup is finitely generated, first of all, you have to remark that if I, the set of indices, which parameters indexes the UIs, is finite, then EK of gamma is just the good old power series ring. Okay. Here, the thing you have to keep in mind is this. You have weights. You want to look at monomials where the weight increases. There are only two ways to make the weight increase. One is to increase the powers, and the other is to add variables with a higher weight. If you have infinitely many variables, you can infinitely many times increase the weight. But if you have finitely many variables, the only possibility to have high weight is to have high powers. So this is essentially what this says. Okay? So, and then this proves that if gamma is finite, my ring is an overweight deformation, as I explained in the beginning. It's enough, because I have everything in hand. I have the power series ring, I have the weight, I have the binomials. What more do you want? I have the overweight deformation. What more do you want? So this proves that finitely generated, we are in the good old case, and therefore I can uniformize. Now, in the 3 minutes that I have left, I will tell you many of the things that, no, it's only 2. Well, the first thing is, so I told you that a Biancar valuation from irrational plus a Biancar, this is equivalent to saying that the Krull dimension of Grö nu R is equal to the dimension of R. But we don't yet know that this is Noetherian, which it is not, in fact, in general. You can have this equality. There are counterexamples due to Kutkowski in the algebraic case, not in the formal case. But there are counterexamples due to Kutkowski which show that you can have an Biancar valuation, but this guy is not finitely generated. But what I proved is that if the ring is complete, you can make toric modification. You can make a modification, not necessarily toric, such that after completion, the semigroup is finitely generated. So for the problem of local uniformization, after some blowing ups, let us say, and localization at the center of the valuation, you get a finitely generated semigroup. You see, it's hard to imagine that a semigroup which is not finitely generated, you enlarge it in the right way, and it becomes finitely generated. But this happens. This happens. So we are reduced to the finitely generated case, and everything is okay. Now, the next thing to look at is, suppose my ring is not complete. Huh? So then that's another result. So this is the first result, which one needs. And the second result, which one needs, is that if I have a rational valuation on a ring R, which is excellent now, in addition to all the other qualities, then you can extend the valuation nu to a valuation nu hat on a quotient of its completion, but that's okay, it's still a complete local ring, in such a way that the Grö nu R and Grö nu hat R hat over H are birational. There are other examples of Kutkowski more recently, which show that, well, which say essentially this is the best one can hope for, assuming that R is, well, no. This is essentially the best one can hope for if one wants to keep looking at regular local rings only. But this is another story. Why is this important? Because here I have, let us say, generators. Let's call them eta I bar. Here I have psi I bar. And what the birational tells me is that eta I bar are Laurent monomial in the xi's. Okay, Laurent monomials. But it tells me that if I make a toric map based on etas in this ring if I make a toric map based on etas in this ring, I can convert it into a toric map based on xi's in this ring. So what this means geometrically is that if I can find a formal embedding into some affine space where a toric map resolves, then I can also find an algebraic embedding, maybe a different one, because I have this Laurent monomial problem, but I can find another affine embedding where the transfiguration of the same toric map, of that toric map, will resolve. So it's a theorem of algebraization. It's always a basic problem in, I think I told you in the beginning, when you think about resolution of singularities. Time's up.